In this question, they have stated that both the bodies have some radius, and again they have mentioned that the distance between the bodies is 1 meter. In that sense, if you take that way, because generally we measure the distance between the bodies from the center of one body to the other body. So anyway, I'm neglecting the radius. I'm just taking the distance between both the bodies from their own centers. If you check your numerical once again, generally the distance between any two body will be always from the center of one body to the center of the other body. Have you copied, boys?
Yes, I'm done.
Shall I move for the next one? Gravitational potential. I think so. I'll redo what is gravitational potential and then we'll start doing the numerical again. Now, what is gravitational potential? Suppose I have a body, say of mass m. Now this is going to create a gravitational field. So in this field, at point P, which is at a distance of r, I want to find what is the potential at this point. What is the potential means? What is the capacity of a body which is placed at point P would have? What is the gravitational potential at point P? For that, let me imagine a mass of 1 kilogram, means a unit mass. Let me imagine a body of mass, unit mass is placed at infinity. The work you do in bringing this mass from infinity to point P. Now this work is a measure of the potential at point P. With respect to the gravitational field created by this mass m. So a mass m creates a gravitational field. In this gravitational field, I want to find what is the potential at point P, which is at the distance of r from its center. For that, let me imagine a mass of 1 kilogram is initially at infinity. You need to bring this mass from infinity to the point P. Right? So there is a force of attraction, gravitation, that is a force of attraction. So you're doing a work in bringing the body from infinity to this point. Whatever work you do will be a measure of potential at this point P. Is that clear, boys? So how will I write V? The gravitational potential will be the work done in bringing a unit mass from infinity to this point. Right? So what is work done? Force into distance. Okay. Force into distance by mass. What is the force? Force will be G because it's a attractive force by R squared into R divided by M. Right? So V becomes this R minus Gm divided by R. This is the potential at point P. Now we'll go for the numerical. What was your numerical? You have a body of 100 kilogram placed at point A. You have a body of 100 kilogram placed at. Now I have to find what is the potential at point P. It's a vector quantity, boys. This distance is 0.5 meter. This distance is. So what you need to find? Total potential at point P. So that is V total will be equal to VA plus VB. The potential at point P due to a mass at point A, VA. Clear, boys? What is the general formula? What is the general formula? What is the general formula?
Work by mass.
V is equal to minus G M divided by R.
Ma'am, why is the
So
negative?
now you, yes, what? Negative is because the force is the force of attraction over here. So
Ma'am, which question are we doing right now?
The same question, second part.
Oh, okay.
Previous question has two parts, boys. So now what is VA? Minus G into, what is the mass which is located at A? 100. Okay. What is the distance? I want to find the potential at point P due to A. So what is the distance between them? AP squared?
Yes.
Okay. What is VB? Minus G into the same mass 100 divided by VP squared.
Ma'am, no square here.
Sorry. Now, then what is V? Minus G into 100 divided by 0.5 minus G into 100 divided by, so V is equal to minus 2G into 100 divided by 0.5. So I can write 2 into 100,000 G because I'm making this as a whole number. So this goes 200. So V becomes equal to 4 minus negative sign minus 400 G. You can substitute the value of G. What will be the SI unit? What will be the SI unit? What is what is gravitational potential? The work done in bringing a mass, unit mass from infinity to that point. So work divided by mass. What is that?
Ma'am, joules per kilogram. Ma'am, potential is not a vector quantity, gravitational potential.
Gravitational potential is a scalar quantity. It's work done. Potential energy is also a scalar quantity. Only electric field intensity is a vector quantity.
Ma'am, out of all of the things that we've derived, is only gravitational field intensity vector?
That's a vector, boys.
Okay.
Because E vector is equal to F vector by M. This is work done.
Ma'am, why don't we include the radius of the spheres?
No, the thing is that they have stated that both the bodies are placed 1 meters apart. Generally, when we measure the distance, when we specify the distance, it should be always from the center to the other center. So that's the reason I have neglected the radius. Or else you have to add the radius.
Yes, ma'am.
Ma'am, can you tell the unit of gravitational potential energy?
That will be joules.
Okay.
So work done. One more numerical. Should I go for it? It will be a bit tedious. Shall I go for it?
Ma'am, 12 minutes are left. It depends on you.
Okay. No, it takes so much of time now complete. Anyway, I'll finish it off. Then in the last period, I'll start doing your other complete this, boys. 6.6 10 to the power of minus 11. Yeah, you can go for it. Yeah. No, you have to. No, you can substitute and do the values.
Ma'am, we have to solve further.
You need to solve, boys. The
Okay.
value of G is 6.67, 10 to the power of minus 11. Did we do any numerical in Young's modulus, boys? How many numericals? All three numericals completed? So only one numerical have done in Young's modulus. 2.
Ma'am, I think we were on the second one.
So we haven't completed the second one.
You told us we did for steel wire, but you told us to do brass. I think
Okay, okay.
it was like in two parts.
Fine.
Ma'am, like the last question, which is steel wire and brass wire, we have to do that one.
Yes, okay. Because next will be your bulk modulus. Even there we have to solve numericals. Have you completed? So anyway, I'll go for the numerical, the next one. Three-point mass, sorry. Now find the potential energy of a system of 4 particles, each of mass m, placed at the vertices of a square of side L. Also obtain the potential at the center of the square. It's an NCERT text numerical, boys. Now just copy down, because now you will not understand what I have written on the
This is also
board.
a system of
Copy down.
particles.
Yes, system of particles. We completed a numerical on gravitational field intensity. We completed a numerical on gravitational potential. Now I have to go for potential energy. Right, boss? Write the question.
Which question number is this?
I don't remember what. I think it's an old text. It is being written as NCERT. Right? Find the potential energy of a system of 4 particles, each of mass m, placed at the vertices of a square of side L.
Ma'am,
Also obtain, yes,
ma'am, the previous questions were the numericals from gravitation, right?
yes. Even this
Okay,
is
this
also
is
from
a system of parts.
no, all these numericals are gravitation.
Oh, okay, ma'am, got it.
All these numericals are from gravitation.
Oh, okay, ma'am.
Right, boys. Find the potential energy of a system of 4 particles, each of mass m, placed at the vertices of a square of side L. Also obtain the potential at the center of the square, because you
Ma'am.
need to understand the concept. Yes.
Ma'am, the previous answer was minus 20.67 into 10 raised to negative 9.
Yes. Yeah.
Perfect.
Ma'am, we have to substitute the value of G there for the previous
Yes,
question.
you need to substitute. You need to substitute, boss.
Okay, ma'am.
Fine. Now I'll go for an empty
Ma'am, what's
slide.
the question number of this question?
I don't remember what it has been specified. I am checking from an old text, not the one which the revised one.
Okay, ma'am, I'll check it in my textbook.
Now look at the question. The question is, you have a
Ma'am,
configuration.
can you stop presenting?
Is that fine, boys? Is that fine?
Yes, ma'am.
You have a configuration of a square where you have 4 masses, equal masses are placed at the vertices. Boys, you have 4 equal masses placed at the vertices of a square of length of side length L, which means if you want to make all these 4 particles to form a configuration of a square, you have to do a work. the total work done in putting all these masses together, because each mass is going to create its own gravitational field. So if you want to assemble all these four masses at the vertices of a square, to bring this configuration, you have to do a work, and that work will be stored as a potential energy in this system. Are you clear, boys? You have to bring all the four masses together, put them at the vertices of a square of side length L. For this, you need to do a work. Whatever work you do will be stored as the potential energy in the system. The question is, find the potential energy of this system. For that, we'll define the side length. Now let us see what is AB. AB will be equal to BC, which is equal to CD, which is equal to AD. All these lengths are L. But let us go for the diagonal. If I go for the diagonal, it is AC as well as BD. This length is L, this is L. So this will be L squared plus L squared. So that becomes root 2L, which means the diagonal AC must be equal to BD, so which is equal to root 2L. First, let us complete this, then we'll go for the work done. Complete this, boys. Have a rough diagram. Complete this. Now, let us see how we are making this configuration, right, boys? Now, look at this. We'll consider all the four masses are at infinity. All the four masses are infinity. Now, let us bring each and every mass to form a square. Now, in this case, I am bringing a mass m from infinity to point A. What will be the work done? Is there any force? Is any gravitational field existing at point A? It's an empty space, boys. There is an empty space. All four masses were at infinity. I'm bringing the mass, first mass, m, from infinity to point A. Is there any gravitational field? Only when there is a field, there is a force. So here, work done will be equal to, if work done is force into displacement. There is no gravitational field to exert a force. So what is the work done? 0. Are you clear, boys? Are you clear? I'll imagine four masses are initially at infinity. I have to bring each and every mass step by step to point A, B, C, and D. First, let me put the mass at point A. Now, there is no gravitational field, no force. So work done in this case will be equal to, should I put this work done? This work done is a potential energy that is equal to 0. Are you
Yes,
clear?
ma'am.
I'll just put it over here. So for the first case, work done. So UA, I'll put this as 0. Now next one, second case. Second one, I have to bring the other mass and put this at point B. One more mass at point B. Now what is the work done? Is there any work done? Why is it? No, but A is already a mass is at point A. Boys, already there is a mass at point A, right? So this mass is going to create a gravitational field. Okay, so already there is a mass. You have put a mass at point A. So already there is a gravitational field. Now you are bringing another mass from infinity to point B. So now whatever work you do, there is a field that field will apply. So then you're moving, there is a displacement, there is a force. Then there will be a work done. So what is the work done? That work done will be stored as the energy in body at point B. So now that work done, let me put it as VBA, that is equal to UBA. What is the general formula of that? Okay, I'll just put it as UBA. Let me put this as UBA. Now I'll have to go for third. Now next one. Another mass. In that case, I have to do a work. In this case, I have to do a work against both the field. A is creating a field, B is also creating a field. So here work done, W, let me put it as, so here the work done will be equal to WCA plus WCB because your two fields are there. So I can write this as UCA plus UCB. Then what about the fourth one? And I put at point D. Then I have to do a work against all these forces because this is going to create a field. Mass at B is also going to create a field. Mass at C also is going to create a field. So I have to do a work in bringing a mass from infinity to point D. So that for fourth one, it is UDA because you have to do a work against, you have to do a work because of the field created by A. Then you have to do a work because of the field created by B. So BD. Next, you have to create a work due to the field created by
W.
C.
Yeah.
W, that work done is a potential energy, boys. This work done will be a potential energy. I'm just directly going for the potential energy. So that will be DC. So copy down, boys. Next class, I'll just let us finish this and continue with the chapter. Shall I? So I'll continue with this topic.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Why is the meeting still recording?